I want to finish this today and do some simple example I wish I can do. So we have a vector potential. What is our footsteps here? What are our footsteps? So we have vector potential. We can calculate the B. We can calculate the magnetic induction and H, taking the curl of the vector potential. But so far, I know one thing. At far field, they are behaving as spherical waves. Propagation, E and H mutually orthogonal to each other. And another thing, instead of curl operator, I can write n cross. We saw this when we are studying the plane waves. And you can do the same thing here. So basically, B is mu 0 H, that is curl of E, and H is 1 over mu 0. Instead of curl, I will directly take the IK n cross with A. So basically, it is IK n cross A. So one thing is this, okay? So as if in the plane waves, instead of curl operator, I can write IK cross. The second, I know I can calculate the E if I need it very easily. The electric field will be IZ0 over K curl of H. And altogether that will be what? IZ0 over K, and so you can do this. That will be minus Z0 mu 0 K, and we have, sorry about this, so let us write this in a formal way. So IZ0 over K, instead of curl, I can write IK n cross, and instead of H, I can write 1 over mu 0 IK n cross A. So one of the k's will be cancelled, and you will obtain minus I Z0 over mu n cross A. So basically, you can calculate the electric field B. You can calculate that the H and electric field Poynting vector, power emitted per Solt angle. So H field, if you go a far field, basically you will drop to the 1 over r square term. If you go to the far field enough, you will drop it and apply this cross product, and your result will be IK over mu 0 n cross minus mu 0 j k square over 8 pi spherical wave term charge density x prime and dot x prime liquid x prime. So this part is the vector potential at the far field. I am picking up to the spherical wave term because that radiation survives at infinity. If you calculate the power at the infinity, that term survives. 1 over r square dies. Why? Because your sphere, big sphere, goes as r square. Your field goes E times B E cross H. Magnitude goes 1 over r square. R square over r square is cancel out, so the wave can propagate to the infinity. Now, so next thing, we will write the H and evaluate the H, as I said earlier, in terms of something we know that now will be the quadrupole moment tensor. I am telling in advance. So we have minus I k cube C. So if you collect the coefficients, you will have IC k cube over 8 pi e to the IKR over R. And so let me take n cross, and the rest is x prime n dot x prime charge density d cube x prime. So again, I'm going to do some kind of semi-derivation here with the trick is the following. So consider the only alpha component of this. Write in terms of indices. Write in terms of the indices. Just the alpha component, not a vector. And you have that term, okay, in terms of indices for alpha component, okay. So do write this in the following form. Say x prime alpha, x prime beta, and subtract a term and add a term, multiply this, 3, divide by 3, okay, and subtract a term, x prime alpha, x prime beta, chronicle delta, alpha beta. What is left? M beta is left. Since I subtract a term, I should add the same terms, but I forget to write at the charge density. Charge density and beta d cube x prime. Since I subtract a term, let me add a term, the same term here. X prime alpha, x prime beta, chronicle delta alpha beta, charge density and beta d cube x prime. So what I did, let me tell you, I write the alpha component. I write this in terms of indices beta and beta. So 1 beta is here, and here's n beta is there. I subtract it and add a term. This term is 0 when alpha is not equal to beta. When alpha is not equal to beta. When alpha is equal to beta, if you sum through the alpha and beta, what you are going to obtain? You will get n vector. The vector will be along the direction of n. And if you cross product with this term, that will be 0. Okay? Therefore, there is nothing wrong adding this 0 and subtracting the 0. But this is useful because we are seeing here the definition of something we know in the past. So let me take the n beta outside, d cube x prime inside. This stuff here is something you know in the past, this integral in the first part. Do you remember that this part? 3 x alpha prime x beta prime minus x prime alpha x prime beta chronicle delta alpha beta times charge density integrated through the volume. This is from chapter 4, from the first part. This is a quadrupole moment tensor. Definition of the quadrupole moment tensor. So Q alpha beta, and it is a quadrupole moment tensor. So what is Q alpha beta sum with beta Q alpha? Okay, if you sum, this is a tensor, second term. This is depending on the alpha beta. And beta is the dummy indices. If you sum through the beta, that will be the Q alpha. If Q alpha is 1, 2, 3, if you add up the components, that is a Q vector. So, and therefore, that is nothing but the Q. So H is equal to, H field is equal to minus IC K cube over 8 pi e to the IKR over R n cross Q over 3. And Q alpha is Q alpha beta. In for normal presentation, I should put a summation I1 to 3. I skipped the summation over there, but I put it here. Okay. So this is a quadrupole moment tensor. If you look at the chapter 4, one of the early equations, 4.9. So see equation 4.9. So that is the heart of that chapter, chapter 4. Very important part of that chapter. So H could be written in terms of Q. Q is related with the quadrupole moment tensor. If I know the H, I can calculate the electric field. I can calculate the Poynting vector and the power emitted per Solt angle. So the result will be in terms of the Q. And what is the Q for a given charge distribution? So let me calculate that the power emitted per Solt angle. So basically what I needed, H. In practical application, I will need a Q alpha beta, that is electric quadrupole moment tensor. But let me show you how I am going to calculate the power emitted per Solt angle. So remember the standard definition of the power emitted per Solt angle, 1 over 2 real part of R square and that E cross H complex conjugate, and that is equal to 1 over 2 real part of R square, and that instead of electric field I can write E Z0 over K curl of H. This is the electric field, cross product with H complex conjugate, And instead of curl operator, I can write IKN. So let me write one more step quickly. 1 over 2 real part r square n dot I z0 over k, and that will be IK n cross h complex conjugate. Too many cross products. So k will be cancel, I and I will be minus. And where is my impedance? Is here. So minus z0 over 2 r square real part of, then the cross products. How many cross products? We have n dot n cross h cross h complex conjugate. Okay, actually I should put this inside the parentheses because this is coming from here. So k's will be cancelled, I and I is minus, z0 is here, so everything is here there. So it seems to be complicated, but it's not complicated, this double cross product. So think about the volume of the 3 vector A dot B. Let's say this is B cross C. Actually, this is complex, so I have to be careful. So think about the A dot B cross C. This is equal to B dot C cross A, and B dot C cross A is equal to N cross H dot C cross H complex conjugate dot cross N. Okay? I call this stuff over here as a B. So B dot C cross A is this. If you switch to one order, this negative will be positive. And if you put the value of the H, where is the H? H is there. What you are going to obtain? Power emitted per Solt angle. Power emitted per Solt angle will be what? Again, one of the nice things, this is a spherical wave. If you take the square of this r square term, and that r square term will be cancelled. So all the times that will be cancelled. If you switch the order, you have a negative sign. There is a negative sign that will be positive. So result will be the following. Square all bunch with a positive sign. C square Z0 k to the 6, and you take the square of 64 multiplied by 2 multiplied by 9, that should be 1152 pi square, and the rest will be what? N cross Q, and so that should be what? There should be, this term is nothing but N cross H magnitude, and H is related to N cross Q, so that should be equal to N cross Q cross N. So let me do it again. Take the square, C square, k to the 6, 64 times 9 times 2, that should be 1152 pi square. E to the IKR is unity, magnitude, and this is 1 over r square, cancels with the r square, and the leftover term, N cross H magnitude, and N cross H magnitude is nothing but N cross Q, or you can switch the order, it doesn't matter, you can write in that form. So the question, this is the power emitted per Solt angle, and the question here, how we can apply practically to the system. We have one more step, then we can do the application. The one more step is the following. Do you have any question here? Okay. So one more step, calculate the N cross Q cross N. Let me do this again very quickly. N cross Q cross N dot product with the complex conjugate, and unit vector is a real, and this will be the following. So if you open this, that is minus Q dot N A dot B along N plus A dot C N dot N along Q. That product with the complex conjugate, that will be minus Q complex conjugate dot N along N plus N dot N along Q. So I write that the double cross product, take this to the other side, and that Q, this will be the that. So if it is the minus correct, incorrect, so in both sides that will be the incorrect. The result doesn't affect it. This is 1. This is 1. So if you look at this scalar product, so that will be that term will be what? Q dot N square, Q dot N times Q dot N square. So is this right? So it's not right. So that should be Q dot N, Q complex conjugate dot N. That is the first term. And if you do this, the second term, there should be minus, this is Q complex conjugate, there should be Q dot N, Q complex conjugate dot N. That is the second term with minus. And if you do this term, that is again one more minus, Q complex conjugate dot N and Q dot N. And if you do the third term, fourth term, that should be plus Q dot Q complex conjugate. So one of the terms will be cancelled, and the leftover will be the 1. And altogether, this is nothing but Q complex conjugate dot Q minus N dot Q square. So this is Q dot Q complex conjugate, and the rest will be magnitude of N dot Q square. So you can go over this. So let us do practical example. So result is correct. You can look and confirm the result by yourself. For me, the important thing, how you can evaluate this. And first, what is the quadrupole? In order to understand the quadrupole, you should look at the quadrupole moment. If it is not 0, of course, it's a quadrupole. But you can, from the charge distribution, you can, you have a feeling that you can have a feeling that whether the system is quadrupole or not. So if we have a charge and charge plus q and minus q, this is, what is this? Dipole. If you put one of them to the next to it, is it a quadrupole? Maybe. So you have two dipoles. You have to look at the quadrupole moment. But if you have one dipole up, one is down, the electric dipole moment of this is 0. One is up, one is down. So only the term should be quadrupole term should survive. In that case, this is more complicated. That could have both dipole and quadrupole terms. So you have to look at the electric dipole moment and quadrupole moments, because you have one dipole here, another dipole unit here. Some of them is a dipole, but to be sure we have to look at. But here it's the one kind of example of the quadrupole. Another typical quadrupole is the following. So suppose this is a one charge here, minus q, and in the middle you have plus q, and here minus q. If you look at here, you have two dipoles, but the net dipole moment is 0, because one dipole is down, one is up. So if you sum up them, that will be 0, and you will have only quadrupole. This is one typical quadrupole. Total charge is 0. Suppose that these charges are changing somehow with frequency omega in time. And suppose that they are separated by amount of A. Suppose that they are separated by amount of A. How we can calculate that the quadrupole moment, and how we can calculate that the emitted power per Solti angle, how we can calculate that the total emitted power. In order to do this, you have to calculate that the Q alpha beta, then Q, then this, okay? Basically, you have to work with the quadrupole moment tensor. So let me write that the definition of the quadrupole moment tensor again. 3 x alpha x beta times chronicle delta r square alpha beta charge density d cube x prime. So one thing here, I write here instead of r square. R square defines that the location of the charge. Because you can write this x alpha beta when alpha is equal to beta, that is x square or r square. So x or x prime are dummy. You can say x prime, r prime, so on, or just x. So this is just dummy integration, okay? But practically, it is related with the location of the charges or charge densities. So if you call that the vertical is the z, then charge density is simple. So let us write that the charge density. Charge density in one dimension will be what? Minus q charge. So let us say that this is the origin. So just the charge is thing, z is thing at the center, and this is up by amount I, and this is down by amount A. So then that means that your charge density will be what? Minus q delta z minus A represents this charge when z equal to A, and plus 2q when charge is the origin, z minus A, minus q delta z plus A. But this is not sufficient. This is in one dimension along z-axis. Along x and y, xy's are 0. So for xy's, write delta x 0, delta y 0. Okay? So this is the charge density. So So this is thing at z equal to a, x equal to 0, and y equal to 0. This is at the origin. This is at z equal to minus a. So why it's the charge density? Because if you integrate this, you can find the charges. Okay, delta function is understandable under the integration of whatever you are working here. We are working with the space, therefore there should be the charge density. So this is the charge density, and how I can calculate that the quadrupole moment tensor. So let us do one practice. So QZZ, for example. So QZZ, what should be the result of the QZZ? Alpha is Z, beta is Z, and Z are the same, that is not equal to 0. So if you do this, this is nothing but, let me do 3z square minus x square plus y square plus z square, that is r square, times charge density minus q delta z minus a plus 2q delta z equal to 0 minus q delta z is at minus a. Integrate this, and what I forget, delta x, delta y, integrate this dx, dy, dz. Okay? I have charge density, volume element, and one particular component of the electric quadrupole moment tensor. So if you take the integral, what you are going to obtain? For the z integral, you will have a square. For the z integral here, you will have a square. For the x and y integrals, what you are going to obtain? X will be 0, y will be 0, because delta x and delta y, they are at the origin. So if you take the integral, you will get 0 for xy, and for z, that will be non-zero. That will be a square. And for this one, what you are going to obtain for that one? If you take this integral through the z, z will be 0. Then that will be 0, z will be 0, z will be 0, xy all the time 0. So if you do that integral, you will get a very easy result. QZZ will be 3a square minus a square. This is true for minus q for the first integral. That is true for the last integral, third integral. But for the middle one, that will be totally 0. So you will get that, and that is minus 4a square q. So all you have to do, you have to be able to calculate that the electric quadrupole moment tensor. So what are the qxy quickly? What are the qxy? This should be what? Qxy. So this should be x, this should be y. So if you calculate for xy, so let me do xy, for example. xy. Oh. So then this delta function will be what? 0, because alpha is different than beta. This is x, this is y, this term 0. What we are going to obtain, this term is 0. X will be 0, y will be 0. So qxy will be 0. Similarly, all cross terms will be 0. Qxz and qyz, whatever you think, will be 0. All cross terms. So what terms will not be 0? Qxx. So let us look at the qxx. We have 3 x square. Alpha is equal to beta, that I can write x square plus y square plus z square. What is the result of this integral, qxx? What is the result of this integral? If you take this one, delta x integral will bring you 0. This one also 0, this one is 0. For that integral, z minus a, this will be only surviving term. So you will particularly obtain minus q minus a square times q for the first one. And what about the other one for this one? When you perform this integral, everything is 0. X equal to 0, y equal to 0, z equal to 0. For the third integral here, again, x and y's, all x, y's will be 0, z will be survive. So you will have again one more the same term, and that should be minus 2a square q. So clear? So qzz is minus 4a square q. qxx is minus 2a square q. If you calculate the qyy, what you are going to obtain? Same, yes. Now, let me write the quadrupole moment tensor for this example. So let me erase the integrals. So electric quadrupole moment tensor will be what? qxx. What is the qxx? Minus 2a square q, 0, 0, 0, qyy minus 2a square q, 0, qzz minus 4. Is it minus or plus? I have a mistake here, I will correct. One term should be the positive. Which term should be the positive? This term should be positive. Why it is positive? Why it is positive? If you look at the definition here, this integral is surviving at minus q charges, and there's a minus sign here. Okay, that should be positive. That should be positive. So this is q alpha beta for this example. Actually, I could write this more clearly in the following form. What I need to calculate, so I think I don't have time to do, I need to calculate the q alpha. In order to calculate that the q alpha, what I needed, qxx I have, qyy I have, qzz I have. And summing up with m beta means that is a column unit vector nx, ny, and z. And this will give you the components of qx, qy, QZ. So if I try to calculate Q dot Q complex conjugate N dot Q, I will not be able to finish. So at this point, we have the quadrupole moment tensor. For this kind of particle radiation, we calculated the electric quadrupole moments. And next time, I will calculate the Q vector, elements of the Q, and I will plug inside, and I will obtain the radiation pattern. And as you guess, in the radiation pattern, I will have 4 poles instead of 2. In dipole radiation, we have 2 poles. It was proportional to magnetic dipole moment or electric dipole moment times the sine square theta. But here we will have 4 poles, so we will have 4 maxima along the angular distributions. So this part will take maybe 20 minutes or so on in the next time. Then I will start the multiple expansion of the electromagnetic radiation.